Hello everyone. We are in the midst of discussing probabilities and more specifically basic counting. This video will cover the concepts of permutations and combinations, which are two counting techniques. In the previous video on basic counting, we introduced the multiplication principle. The counting techniques that you will see in this segment are a natural follow-up to the multiplication principle with slight variations. I'm going to start off by discussing permutations and arrangements. Now, by definition, we call arrangement the number of ways or the number of orders in which n elements can be placed into n spots without repetition. In other words, arrangements count every way to scramble n elements that are considered distinct. According to the multiplication principle, this means that the arrangements of n elements leads to n choices of the element that will be placed first, n minus 1 second, n minus 2 third, and since all the elements are eventually positioned in specific spots, we'll eventually have 3 left to place, and then 2, and then 1. So obviously the last element is the last one that was selected. So this product of n times n minus 1 times n minus 2 times 3 times 2 times 1 are all distinct outcomes because of the orderings in which they are obtained. Of course, instead of writing the product of all these different numbers, we could just say n factorial, which is a shorthand notation to represent the product of all numbers from 1 to n. For example, how many 7-letter words, whether they exist or not, can be formed by scrambling the letters A, C, F, H, O, P, S? So we've got 7 letters to place. We're not allowed to reuse any of them. Think of these as Scrabble tiles that you're going to form words with or attempt to form words with. Okay. So since there are 7 letters to be placed into 7 spots to form a word, then there are 7 factorial, so 5040 arrangements. Every letter has to be used once, exactly once, and the order will generate a different outcome, in this case a different word. As a second step, we can define a permutation. So we call permutation the number of ways to place or to order r elements that were selected from a list of n elements without repetition. So in other words, permutations count every way we can pick and place r elements that were taken from a set of n elements. I'm assuming, obviously, that r is no bigger than n. According to the multiplication principle, this means that the permutations of r elements selected from n leads to the following product. So there are n elements to pick from when we make our first selection. There are n minus 1 left to pick from when we make our second selection. And we continue in that way until there are n minus r plus 1 elements left to pick from when we make our rth selection. So this product is the number of different outcomes that will occur. Observe that by the time we're done, there are n minus r elements that have not been used. Okay, so it's hard to count, but the product of the numbers that were listed above, n times n minus r times dot 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 until n minus r plus 1, there are actually r terms in there, and n minus r are left out. Mathematically, this sequence or this product of terms can actually be written differently. So what we can do is, notice how in red I've completed the sequence of products, so I'm decreasing by 1 the number of choices that are left. Because I'm multiplying by numbers that were not there in the first place, I also divide by those same numbers, and by doing so, at the numerator I've created a product from 1 to n, which is basically a factorial. And at the bottom, we also have a product of 1 all the way to n minus r. So essentially, this is the quotient of n factorial over n minus r factorial. In terms of notation, the permutation of r elements selected from n elements is denoted by npr. So this is a way of just summarizing the fact we're doing a permutation without having to list a really long sequence of numbers multiplying one another. So npr will stand for n factorial over n minus r factorial. In terms of reading it, we say n permute r. So npr, n permute r elements. For example, how many 5-letter words, whether they exist or not, can be formed by choosing and scrambling the letters A, C, F, H, O, P, S. So the same letters that we had before, the same 7 letters. How many different 5-letter words? I guess there are 2 things happening here. We have to select the letters that will form our 5-letter word, and then we could also scramble them. Okay, so ordering is important. There's no repetition. And we're permuting 5 letters selected from 7. So 5 letters to be selected from 7 without repetition. So if you actually listed things out, you would have 7 letters to choose from to form the first letter of your word, 6 for the second letter, 5 for the third, 4 for the fourth letter, and 3 for the 5th letter of the word. But notice how I've completed the factorial term by multiplying by 2 times 1 and dividing by 2 times 1. So 7 factorial over 2 factorial, you probably recognize fits what we called a permutation earlier. Okay, so it would have been faster actually just to say from the start 7 permute 5. So from 7 things to choose from, select 5 and place them in all possible orders. So 2,520 different 5-letter words. Probably 3 of which really exist, but whatever, that's not what we're really concerned with here. Finally, there are combinations. So we call combination the number of ways to select r elements from a list of n distinct elements. So far it sounds a lot like a permutation, but without repetition and without regard to order. In other words, combinations count how many ways distinct sets of r elements can be chosen from a set of n elements without really worrying about the order in which these elements were selected. We've already seen that n permute r calculates the number of ways r elements are selected from a set of n and placed in a specific order. However, keep in mind that this quantity therefore calculates all the shufflings, so all the rearrangements of the r elements as being distinct. There are in fact r factorial different ways to move the letters or the elements that we selected. And they're all equivalent when we consider counting through combinations, because combinations wants to disregard a difference in order. So the number of combinations is actually the number of permutations that we divide by r factorial. Because once again, for every permutation includes orders that the combinations do not. Okay, so we're unscrambling in the case of combinations. We're removing the effect of order. The combination of elements selected from n elements is denoted by NCR. So notice how the formula resembles a little bit that of a permutation, but with that extra r factorial divider. Again, the purpose of that r factorial divider is to remove the repetitive nature of the scramblings of the same elements, because we don't want to consider different orders as being different outcomes. We read NCR as n choose r. So you see already the word permute and choose makes a big difference in terms of how we count. For example, a class has to select a committee to represent them at a student union meeting. How many 5-member committees can be formed by choosing 5 elements from a group of 30 students? So 5 representatives are to be selected from a set of 30. Obviously, there are no repetitions. The same student cannot be selected 2 or 3 or 4 times on this committee. And there is no regard to order. We're going to send a 5-member committee with as a group. So the outcome will be 30 choose 5. So from 30 elements, choose 5 to act as your representatives. That's 142,506 different possibilities. Just to show how the effect of combining is different from permuting, in this previous example, if we had order to the selection, so for instance, if the representatives also had to occupy roles on the committee, then the role each person assumes plays or has an impact on the type of committee we get. So if person number A is a very good president, well, putting person A as the secretary will create a 5-member committee that's different. So that would have been a permutation if hierarchy was given, if a role was given. So 30 permute 5 increases by 5 factorial the number of different arrangements a certain committee can have. So we would have gone to 17,100,720 different